whole thing. Okay, now that we've had some fun, and if you're like me, yes, you'll continue to have fun. I've lectured a few times wearing these glasses, but it gets a little bit difficult after a while.
Wait, so I have a question.
Yes?
If this was not like 3D glasses, what's the difference between this and 3D glasses?
Actually, there's a huge difference between this and 3D glasses. 3D glasses, no, it's a good question. 3D glasses have one basic thing they're trying to do. They're trying to make it so your left eye and your right eye see different things. Toussaint, yes. You want to go in there? I have a cupboard open, like the next to last one, and it's got like 15 3D glasses. You want to grab a handful? We want our left eye and our right eye to see different pictures. Because for us to have depth perception, we have to actually multiple ways that we perceive depth. The first way that we perceive depth is the obvious way, the one they're trying to trick. We perceive depth by triangulation, the angle that our eyes are going. And that's the one they're trying to trick with the 3D glasses. Another way that we actually perceive depth is because our eyes are constantly, A, moving all about, and B, they're focusing in and out. And for that focusing in and out and moving about, we also get some 3D vision. So a person with only one eye does have some very limited 3D vision. But a person with two eyes, binocular vision, has much better 3D vision because you have the angles. So what they want to do with the 3D movie is make it so this eye sees one image and this side sees another. And then things are shifted in position a little. So I have like, let's take what's happening right now. If I look at Anne, I see this eye this direction, this eye that direction for Anne. But if I look at Michaela, each one's looking out just a little further. And so they take images and they shift the positions of things, or actually they do it naturally. They take cameras and have the cameras mounted separately. So they have different angles, and thus things are shifted in position just a little bit. But you have to make sure the right eye gets the picture for the right eye, the left eye gets the picture for the left eye. I must have closed the cabinet in there. You would have been back by now. So, methods for getting that 3D effect. One method that you may have seen, I clearly closed it. It's in the count. Well, I'll just grab one. Dead space on the recording, fill it in. Some nice things.
These glasses are cool.
Yeah, there you go.
Can I pass?
Yeah. The colors make different. Oh, you want to do two of them?
Does dual motions not have rainbows?
Okay. These glasses are also cool. Wow. But these glasses are using polarization.
Well, what if you do the glasses and the diffraction?
If you what?
If you use this one and this
Well, this one here, it just makes you see a second image off to the side. And the distance for that is based on color. And so you just see multiple images, but it's not really going to give you the depth. With the oldest 3D glasses, you might have seen these days, you'd have to watch something like Bachelor Party, where they show people a 3D theater. They're wearing glasses that look a lot like the ones you're wearing. But one lens is green and one is red. I thought they were green and red, I don't know. I have a Sports Illustrated that has green and red. That's why I'm going green and red. And then they have, the colors are actually modified so that you have extra green on for one eye, extra blue for the other, or something like that. And so that's how they're deciding which eye sees which. So that's the oldest form I know of 3D movies. Then if you go to the IMAX theater over at the zoo. Yeah, the zoo. In Omaha. Yes. Henry Dorley. Yeah, there you go. Henry Dorley. If you go over there, I believe theirs use straight polarizers, regular old polarizers, like the kind that I was using here. If you go to a real 3D movie, they use these things. And these are more complicated. We call this circularly polarized light. What they do is they actually put in a little plate that causes a delay for one polarization direction compared to the other. So like we saw with the calcite crystal, it's separating the polarizations by time. And then because they're separated by time, you actually have the electric fields go around in loops like this as they travel to you. And they can either delay it so it goes clockwise or counterclockwise. And so one of these eyes is right polarized, counterclockwise. One of them is left polarized, clockwise. So I'm going to have my friend Ann wear glasses. Now, this has a polarizer and a quarter wave plate, I think it is. Hers has a polarizer and a quarter wave plate. Now here's what I'm going to have her do. I'm going to have her close one eye and then look at my eyes with the other eye. What do you see?
One is black and one is clear.
One is black and one is clear. Because the process is being reversed or done with the lenses. So my eye is putting out unpolarized light, it goes through this lens, and it becomes circularly polarized. And one of the lenses will take that circularly polarized light and recombine back to normal. The other one will rotate by another 90 and completely block it. And so if she closes her left eye, right eye, she closes her right eye, her left eye will see my left eye, and vice versa. And so that's how they're controlling it. And the reason they do this circularly polarized instead of just straight polarizers is because I can go like this and go sideways, and I'll still have the same effect. Whereas if you have straight polarizers, you rotate your head and you lose the 3D effect. So these are also cool. So those are different methods to achieve the 3D that you asked about. There is one more that was famously used in Married with Children, and that is actually using the Pulfrung effect, the effect that if you have less light, you have a delay in the image processing. And so they had things moving sideways, and you were supposed to wear these glasses that were essentially sunglasses with one knocked out. And so the things moving sideways, the faster they were, the further it looked like they were toward you or away from you, depending on which direction they were going. And so you just had moving things would appear in front or in back. It was really lame. But they did it. Okay, today we're looking at things that clearly indicate that light is a wave. So we talked about polarization for the first half of our class. Now we're going to talk about Young's double slit experiment. Now just a little history that was very briefly mentioned in the lab guide. Earliest theories of light said things like light's, you have tentacles that come out of your eyes. We talked about that. And then we get to Sir Isaac Newton. And Sir Isaac Newton said, I believe that light is particles, that it's like BBs. And so there are BBs coming, and they come into my eyeball, and it focuses those BBs, and that's what I've seen. Particles of light. And, Sir Isaac Newton was a pretty wise dude. And so people pretty much adopted that. Yeah, it makes sense. He explained refraction, although technically he did it wrong, using the particles, and, he did explain a lot of things. Not the stuff we're doing today, though. Sir Thomas Young did his famous double slit experiment. The first slit there is because you need to have coherent light. And by making this tiny slit, you can restrict it so it's approximately coherent. So then you have that coherent light that goes through two slits. And as we saw up here, what did he see when he had the light go through two slits? Yeah, he saw multiple bright and dark spots. Now think about what would happen if I had two slits cut in a fence. And I'm out here with my BB gun or my shotgun, and I'm taking pot shots at it. If the BBs hit the slit, they go through. If they miss the slit, they don't go through. Pretty simple, right? And so what am I going to see on the wall behind my two slits? I should just see the image of two slits, if it's particles. If you see multiple slits, that doesn't fit at all with particles. And so this experiment done by Thomas Young, the double slit experiment, is absolutely vital for our understanding of light because it shows that light has to behave as a wave. So he does this experiment, and everybody's all, oh, Newton was wrong. He was wrong. Light's not a particle, light's a wave. And so what we're looking at today in the lab are things that are specifically wave nature of light. Things that light has to be a wave if it's going to do this. The polarization you can't polarize the particles. If I have electrons shooting at you, there's no vertical or horizontal or anything on it. They're just traveling, right? You have to have a wave to be able to polarize. For this to work, to get the... Really? It's been a long time, apparently, since I've touched my screen. For this double slit experiment to work, you have to have waves. So let's look at how the waves work to give us the pretty patterns. So first, we're going to review constructive and destructive interference. We talked about it a little bit yesterday because we talked about the constructive and destructive interference that occurs with thin films. We talked about it much more extensively first semester. So here we have two waves, a green wave and a blue wave that are in phase. What did it mean for them to be in phase? Reach their peaks at the same time, the same location. And so if I have these two waves that are in phase, the amplitudes simply add up. So the red curve here is showing adding the two together, and we call this constructive interference because they added to construct something bigger. Of course, we see intensity, so we want to talk about how intensity relates. Now the amplitude is the electric field, right? For an electromagnetic wave. And so the intensity is proportional to the amplitude squared, proportional to the electric field squared. And so if I have two waves and the waves are in phase, then the total amplitude is just the sum of the two original amplitudes. The total electric field is the sum of the two original electric fields. And so the total intensity is just going to be proportional to that sum, and so I square it. But if you square A1 plus A2, you get C times A1 squared plus C times A2 squared plus 2C A1 A2, a cross term here. And so the intensity, if intensity 1 is CA1 squared, intensity 2 is CA2 squared, the total intensity you get is actually bigger than the sum of the intensities. It's intensity 1 plus intensity 2 plus 2 times the square root of the product of the intensities. So that's what happens if you have constructive interference between two waves. Does that make a little sense? Okay, hopefully soon it'll make a lot of sense, but at this point I'm going small. So this is just a summary. If they're in phase, then you either have a path length difference or phase difference of an integer number of wavelengths or 0. Right, so they're all at the peak at the same time. And the amplitude is just the sum of the two, and the intensity is the sum of the intensities plus 2 times the square root of the product. Now let's go to destructive interference. For destructive interference, now I have my green wave and my blue wave are out of phase. They're exactly 180 degrees out of phase, or pi radians out of phase, or 1/2 wavelength out of phase, because when the blue one is at its peak, the green one is at its minimum. But we still just add up the amplitudes. We add up the electric fields. And so the red now is showing adding the electric fields together. And once again, if I add these and I calculate my intensity, because my amplitude is the difference between the two, if I square the difference between the two, I get the sum of the two minus 2 times the square root of the product of the two. So when you have destructive interference, you have a minus sign here. Constructive interference, you had a plus sign there. If you have random light, if you have incoherent light, so there's no phase relationship, then it turns out that those two terms are just going to disappear. I should go back. I'm sorry, you can't answer yet because I haven't moved forward. If we have random incoherent, not uncoherent, then the intensity is equal to intensity 1 plus intensity 2. So you don't have the term that was the product. If they're coherent, you have plus 2 times the square root of the product. If they're out of phase, minus, and if it's incoherent, just that. So our first clicker question of the second half. In the figure are 2 sound sources. Are the 2 sound sources coherent? I'm sorry. Missed the intonation. Okay, I cannot tell. I put in my response grid incorrectly, so it tells me students 10 and 11 haven't answered, but I can't tell who they are. Now it's just 10. Okay, there we go. So the answers we got. We had 0 people that said, yes, they're coherent. 11 people that said no. 1 said part of the time. 5 said at some locations. And 1 said not enough information. Now, let us review what it meant for them to be coherent. If they're coherent, we just had this a moment ago, that means that they are going to reach their peaks at the same time at the same location. Now, when it asks at the sources, it says, okay, so at the source 1 and at the source 2, those are the locations we're comparing. It's not on top of each other in this case. It's at the source 1 location and at the source 2 location. Are they going to hit their peaks at the same time? Okay, I saw some people changing their mind about that because it said in the figure are the sources, and the sources was the key that says you're only evaluating here. And so it doesn't have a location aspect because we're only evaluating there. So I'm going to now re-poll the question to see how people answer with that new bit of info. I am once again waiting on one student number 13. Number 13. Going once, going twice. Oh, just as I was hitting the button, 13 got the answer in. Whoever that is. Okay, so on repolling, 9, 8, 0, thankfully 0, and 1. Okay, smarties. There. Not funny. Okay. Most of the people move toward the correct answer here. That is, at the sources, they are indeed in phase. They're hitting their peaks at the same time at the sources. But as you move away, well, then it depends on the position if they're still going to be coherent or not. But at the sources, they were. So the correct answer was yes, at the sources. Of course, that leads us to the next question. In the figure, how does the sound interfere at the observer? So is it constructive, destructive, or something else at the observer, at that young lady who appears to be completely bored and looking away? Actually, she's turning her ear, so she has the best hearing. Now I'm back to I can see who hasn't answered, Sally and Michael. Okay. 0, 16, 1, 1. The 16 have it. How did they determine that? Because when one is at its maximum, the other one is at its minimum, at the observer. So she is hearing destructive interference, which means it's not very loud. Now notice the path lengths are shown. 3.25 wavelengths and 2.75 wavelengths. What's the difference in the path length? It's 1/2 wavelength difference. Because the sources were in phase, and we have a 1/2 wavelength different for the path length, then when they get to her, they're 1/2 wavelength out of phase. And 1/2 wavelength out of phase, destructive. Integer wavelength in phase, constructive. So it's destructive. Has anybody ever observed this kind of destructive and constructive interference? Where you walk around and the sound gets louder and softer depending on where you are. Few people? Back when I was in graduate school, we used to go to Lower Granite Dam. Go there and try to pretend it's a beach and play volleyball. And you go inside the dam, they have those turbines. They make incredible racket, but as you walk around, some places it's really soft and some places it's really loud. And that's because all of those turbines are going at the same frequency, right? Because you want to make the electricity at the right frequency. So they're all the same frequency. As you move around, you're getting the distances from the sources are varying. In some places, you'll have destructive and some you'll have constructive. And so that was something I thought was really cool. My girlfriend thought it was the stupidest thing in the world. Yes?
The difference in the path was 1 wavelength, then it would be constructive.
That's correct. If the difference in path length was 1 wavelength, it would have been constructive.
Did you also say it was incoherent?
No, not incoherent, because actually incoherent is that you don't have a fixed relationship. And we do have a fixed relationship. So, condition for constructive interference, if you have an integer multiple wavelength difference in path, it's going to be constructive. So that's where we had the question Tori just asked. If it had been 1 wavelength difference, it would have been constructive. If it had been 3 wavelengths difference, it would have been constructive. 2.5 wavelengths different, destructive. And if it's something else like 2.75, well, it's somewhere in between. So for destructive, here's the 1/2 wavelengths. I will spend 0 time on that because I just said it. So if you have 2 paths that aren't in the same medium, that is, as an example, what we did with the Michelson interferometer problem in class yesterday. When we pumped the air out of that chamber, it had different index refraction. You still have to deal with the wavelength difference for the path length. So the wavelength is different in a different medium, hence you count the wavelengths, not the actual distance. And we also did that when we were doing the thin film interference. When the light was going through the water film, we had to have the shorter wavelength because of the slower speed of light. So here is a simple enough problem. You have a microwave source, you have a mirror, and you have a microwave detector. And as you move the mirror forward and backward, you're going to get constructive and destructive interference between, actually you have 2 mirrors. Yeah. As you move the distance between them forward and backward, you can have constructive and destructive interference because of the different path lengths. So I put on here length 1, the path length for a microwave to go from here to here to here is just 2 times this distance. Right, we're assuming there's no up and down, it's just horizontal. Whereas for path 2, to go from here to here to here, you have to go 2 times the distance plus 2 times x. Right, 2 times because you're going out and back. And so the path length difference between the two turns out to be 2x. So we have data now that says when I move my second mirror out at this position here, let's say that's 3.9 centimeters, I have constructive interference. at this distance here, 5.2 centimeters, I have constructive interference again. At this distance here, 6.5 centimeters, I have constructive interference. And so the question is, what's the wavelength of my microwave? Okay, we have a very quick question, or a very quick answer, excuse me. Tell us how you got your answer. I didn't even check myself to see if it was right. Okay, she subtracted the difference and found that we have constructive interference every 1.3 centimeters. Now remember, if I move out 1.3 centimeters, how much did my path length change by? 2.6 centimeters. And what is the difference in path length from constructive interference to constructive interference? Okay, so the difference is going to be a wavelength. And so Tori takes her answer back. What is the wavelength now? Something besides Tori, because she's already told me. What is the wavelength of this microwave? What is the wavelength? Two times 1.3 centimeters. I feel like people weren't really paying attention to what Tori said there. So 2.6 centimeters is the wavelength that we can read directly from that information. This here is the picture on the previous slide, is another kind of interferometer. It's a much simpler interferometer than the Michelson interferometer, but allows you to measure the wavelength in a nice, easy way. And see that the delta L is equal to 2x, and delta L is equal to m lambda for constructive interference. So if the difference in length is 2 times 1.3, to go from one to the next, we increase by one wavelength. Yes, question?
So we're assuming that the paths are perfectly horizontal, basically?
Yes.
If we're not supposed to do that,
If we're not supposed to do that, then we're going to have to use things like Pythagorean theorem or, yeah, because we usually don't. We usually, just like with the thin films, we made the approximation that we're just going straight down and straight back up, not at an angle. Why? Simplification. Okay, example of interference, CDs. Since you guys don't have the experience of cassette tapes, or probably even VCR tapes, this is something that should resonate a little with you. CDs use essentially what we just saw with the microwaves. You have a laser beam that comes up and is focused on the CD, and the CD has some plastic here, and then it has a reflecting surface. And the reflecting surface is different depths. And because it's different depths, you have a different distance that the light has to travel. Different distance it has to travel, you can have constructive or destructive interference with the reflected light and the initial light. And that's what you're actually measuring to get your data off of a CD. It's actually pretty ingenious, isn't it?
Yeah, so how do we burn CDs then?
How do we burn CDs? When you burn CDs, there are different technologies involved with different types of burning CDs, and I don't know all of them. The original ones, the reason they called them burn is they would essentially have a layer that was reflected that you could burn off. And so you burn that off, and then it goes to the other layer. Those you could only burn once, clearly, because you can't heal it. These days, obviously, we have readable writables. You can rewrite all you want. And in that case, I think they have a material that they can actually change the index of refraction, but I don't know. Okay, so back to Young's experiment. Young's experiment, you have two slits, light goes through each slit. According to Huygens' principle, we can treat each opening in the slit as if it's a source of light. And that light is going to be in phase because of the first slit. And so then the light goes through, and as you can see, going from this slit to this point, and this slit to this point, oh, those are perfectly straight lines. I'm going to redraw both of them with my straight line tool so they actually look like straight lines. Those are clearly different lengths. And since they're clearly different lengths, then that means you're going to have a difference in phase because of the different path length. Does that make sense? So our key to determine if it's going to be constructive interference, destructive interference, or something in between is going to be based on geometry to determine what the difference in path length is. Now this picture is nothing close to the actual geometry we use in our calculation. In our calculation, we do the far field approximation. That tool doesn't work out well for writing. Far field approximation. People in physics 252, what do we call that? German dude's name? Fraunhofer. It's Fraunhofer. The far field approximation, that is the separation between slits. Separation has an E between S and P. Separation between slits which we give generally the symbol D, is much less than that's an A, then the distance to the viewing screen. Which in this picture is called D. So lowercase d is much less than capital D. In that situation, now if you look at this picture, you clearly can't make that, that's not true in this picture. This picture is just to make it all fit in one picture. Because if you wanted to make it fit in one picture and be able to see the separation of the slits, you have to have the screen a mile off. So we have an approximation in our picture. But in that approximation, we're going to have essentially this and this are parallel. Right? If the screen is really far away compared to the separation, then the two lines coming from A and B are essentially parallel. Which makes this triangle, as I said to my students earlier this morning, the famous 90-90-0 triangle. Right? This angle at the top, alpha, is approximately 0 degrees. And these two angles down there at the bottom then are both 90 degrees if we just square it off. Is that a correct approximation? Yeah. If this capital D is, let's say, greater than 100 little d, then that's a virtually perfect approximation. So that's the range we're working in. The range where that is a good approximation. This is a greater than sign. So in that approximation, the only difference in the path lengths is going to be this additional piece right here, from where we cut them off at the 90 degrees. And so using just geometry, sine theta is equal to opposite over hypotenuse. So in this triangle, D is the hypotenuse for the right triangle that I will just draw in red. D is the hypotenuse, and my path length difference is the opposite side. And so sine theta is delta L, the path length difference, divided by D. So you solve that for delta L, and you get the path length difference is D sine theta. What condition gives me constructive interference? Delta L is equal to an integer number of wavelengths. That's a Y. So you just substitute that in. D sine theta is equal to m lambda That gives you constructive interference. What about for destructive interference? What was the condition for destructive? Delta L is equal to parentheses m plus 1/2 wavelengths, 1/2 integer wavelengths. So then we have d sine theta is equal to m plus 1/2 wavelength. In both cases, what is m? Any integer, positive or negative. And we call these m's the order. So the 0th order is m equals 0. First order, m equals 1. So on. Actually, when you talk about minima, it gets a little confusing, but just work with that. So here's our equations that I just wrote out. The word order and how it is meaning or used. I actually want to skip over these water analogy ones. Go straight to a problem. A laser is wavelength 690 nanometers, and it's used to eliminate 2 parallel slits. The distance d is 3.30 meters away from the slits, and we have the space between adjacent bright fringes is 1.80 centimeters. Where's say bright? There's bright. And we're asked to find the separation between the slits. How can I approach a problem like this? Of what? Okay, I'm going to have to do something with sine of theta. I have theta 1. How do I calculate what theta 1 is? Or maybe I should ask a more basic question. What is special about theta 1? It's what?
Isn't it supposed to be 0?
No, theta 0 would be 0 degrees, which could. The angle between what's?
The slits?
Not the slits.
The illumination from it?
It's the angle between the bright, we call them fringes. The 0th order bright fringe is at the center, and then the 1st order bright fringe is m equals 1. So theta 1 is the angle for the 1st order bright fringe. So I have my equation that says d sine theta 1 is equal to 1 lambda. Right, the equation was d sine theta sub m is equal to m lambda. Since m numbers the order, I put m in there so we see it's going to be the same thing. Okay, so that's an equation. I need to know what theta 1 is, though. How do I find theta 1? Trigonometry. I have a triangle and I know 2 sides of the triangle. What are the 2 sides I know? Opposite adjacent. What function relates those? Tangent. So this is going to be theta 1 is inverse tangent of the opposite side. What's the value of the opposite side? Okay, 1.80 centimeters. X would have been correct as well. And what's the adjacent side? 3.30 meters. Now, what do I have to be careful about here? Units. So let's rewrite that as inverse tangent of 1.80 centimeters over 330 centimeters, just so that I have the same units. So you put that in your calculator, and you're going to get a really small angle. And what are your units? Degrees, okay? He said radians, now he's embarrassed. That's all. Okay, now I need to find what D is. So now that I found theta, how do I find D?
It's change of length over D, right?
Well,
Sine of theta equals R.
Since I have this equation right here, I just solve it for D.
Okay.
So that's lambda over sine theta 1. So that's going to be 690 nanometers. And what do I get? It's going to be a big number of nanometers.
126,502-ish.
It's what?
Approximately 126,502.
126502. Okay, so 126502 nanometers, that would be equal to 0.1265 millimeters. And so I put it in millimeters to illustrate that it is getting something up to where we can actually discern the separation. So those are our typical types of problems for a double slit interference. So our next clicker question. A laser is used to illuminate two narrow parallel slits. The interference pattern is observed on a distant screen. What happens to the pattern observed if the distance between the slits is slowly decreased? All right, everybody has answered. 1611. Good. People were on top of this. If we slowly decrease D for m lambda to stay the same, then sine theta m has to go up. And since sine theta m goes up as theta goes up, the angles are going to get larger, so they're spaced out more. All right. Even though it's only says slide 37 out of 52, we're getting pretty close to being ready to do the lab. Gratings. Now what you have, if you have one of these still, is a diffraction grating. It's a whole bunch of slits. Now these diffraction gratings have both horizontal and vertical slits. That's why you see patterns in both directions. When we do that, instead of talking about the separation between slits, they usually talk about how many slits per centimeter you have. But note that if they give you slits per centimeter, that's just 1 over the distance between the slits. The equation we just developed is the same equation that works for diffraction grating. But diffraction gratings have a very distinctly different outcome. Why? Because the condition for constructive interference is exactly the same for a double slit as it is for 1,000 slits. But if you're not exactly constructive, if you have 1,000 slits, you're going to have a lot of different variations of constructive and destructive that will average out to 0. So if you have a diffraction grating with a large number of slits, you have destructive interference everywhere except for the points where you have constructive. So we had an equation for destructive interference for the double slit. For a diffraction grating, it's destructive everywhere except where you have constructive. And so that's the real benefit of using the diffraction grating. You have very distinct points. And the more lines per centimeter, the more it's going to spread them out and give you more distinct points. So you use exactly the same equation for maxima, and it's just minima everywhere else. So it's easier to calculate. It's coming. Yeah, just move on beyond that. Here's an example of a very simple usage of these devices. You have light coming from something like, let's say, a telescope. I have a telescope and I'm looking at a star. And I want to look at that light from the star and determine what colors are present. Well, I can use a diffraction grating to separate the different colors. And so this is showing, use diffraction grating, it goes around in 180 degrees from -90 to +90, so you get all of the fringes. And that's giving you all of the colors separated out. Now, one thing to note, this here and this here are the first order. One would be m equals +1, one is m equals -1. Nobody cares if it's +1 or -1, it's the first order. So what do we call this here? The second order. Notice the second order and the third order come together. And you can have the orders overlap. So it's not super simple if you get further out there. They start spreading out more and you can have overlap. I have a clicker question on this, but I hope I took it out. If not, I'll just skip over it anyway. So we got to get started with the lab. This here, well, we'll just do stuff with this later on. I'm going to skip over. We'll do it later. The last thing that I think I'm going to talk about is for practical applications, instead of using a diffraction grating, we often use a reflection grating. What's the difference in a diffraction grating and a reflection grating? The diffraction grating has a bunch of little slits and it's blocking light in between. Right? You have to have something to block it or you don't have it. Oh my God, I do have to go something else after this. The reflection grating has a bunch of mirrors that are all set something like this. Okay, that was supposed to be uniform. It's set this way so that if you have light coming in at a certain angle, they actually call it a blaze angle. If you have light coming at a certain angle, you'll reflect all of the light. You'll have no loss. And so the reflection grating allows you to have less loss and thus better clarity and higher intensity for a weak signal. And so when I was doing my research, that's what we used, reflection gratings in our spectrometer, because you could change it out, blaze for a different angle. Okay, the one thing that I forgot to mention that I have to cover is the single slit. Right? I think we started by looking at the diffraction from a single slit. Diffraction is light bending around corners. Interference is the patterns that you get from the light bending around corners. So everything we've been talking about after we came back was combining diffraction and interference. This here, diffraction from a single slit, we now have light going through a continuous slit, and we have different phases again for the light. Now the way we do this for a non-calculus based class is we say let's divide the slit in half. And for the first half and the second half, you're going to say, okay, I have this ray here and this ray here, and if those two rays are constructive, then I should have a bright spot between those two. The one that's halfway and the one that's the edge. But if that's the case, then as I go across for everyone in the first half, there will be one in the second half that's also constructive. And so we come up with kind of a hand-waving explanation to say that for the single slit, we're going to have constructive interference if this distance here is an integer wavelength. So if I have m lambda is equal to 1/2 the size of the slit sine theta, so So that's what we would get from looking at this picture. Now that's not the full and correct equation. In fact, did I do that right? Yes, the problem is we do destructive rather than constructive, right? It's kind of a hand-waving argument. Did it wrong. If you have destructive between these two, then you'll have destructive between everything from here and everything from there. When you put it together, it turns out that A sine theta equals m lambda for destructive. Now, if you look at what we just did a minute ago, we had d sine theta is equal to m lambda for constructive. So the equation for constructive interference from a double slit is the same as the equation for destructive interference from a single slit. With one exception. This equation here would say that you'd have destructive interference at the center for a single slit. And as we just got to in the Physics 252 class when we had to quit, it turns out that the equation gives you a maximum at the center. So except m equals 0. And for Physics 152 level, we don't talk about where the peaks are, we just talk about where the destructive interferences occur. The peaks are going to be roughly halfway in between, but it's not perfect. So this is what the diffraction pattern from a single slit looks like. It does not come down at the 0, it stays high at the 0. So there's looking at the full thing. How wide is it? Here's the wrong answer for how wide is it. You might tend to think the central width should be the width of the slit. No, that's wrong. And in fact, the narrower you make the slit, the wider the central bright spot is going to be. Because of that, you can just see at the bottom of the screen, let me slide it up a little. Because of that A sine theta is equal to m lambda, then the central bright spot is going from m equals 1 to n equals minus 1. And so that angle depends on lambda over A. So the bigger A is, the smaller angle, the smaller it is. This plays into some really cool things. Like, oh, you've gone to the fair, right? Everyone's gone to the fair, right? Yeah. And at the fair they have these speakers that are shaped with an opening like, yeah. Sound comes out of that opening, and the sound waves diffract from a single slit. Now, from what I just said, if you wanted to diffract a large amount, do you want a narrow slit or a broad slit? Narrow slit to go broad diffraction. If you want it to stay fairly straight ahead of you, do you want it narrow or broad? Broad. So if you're at the fairground, you want to broadcast wide to everything in the fair. But you don't want to broadcast all up into the sky. That's just sound energy that's lost. So you want to keep it narrow for the vertical, but broad for the horizontal. So how do you orient that speaker so that the fairground gets filled up with sound? Well, you have one side is long and one side is short. Do you want the long side vertical or horizontal? You want it vertical, because that's going to limit the vertical spread. You want the narrow side horizontal, so you have a broad horizontal spread. Which seems exactly opposite of what you would have thought, doesn't it? And you generally would have thought, I'll make it broad this way so the sound goes up, like that. But it actually has the opposite effect. Okay, this is where we shall end. So that means stop the recording.